In the last tenth of a second, the time it took you to blink just now, quantum mechanics suggests you were not fully here, not in the way you think you are, not as a solid, definite thing occupying a fixed point in space. According to the equations that govern every atom in your body, you exist as a spread of probabilities until something or someone forces a measurement. This is not philosophy. This is not metaphor. This is what the math says. And it started with a 23-year-old sitting alone on a barren island in the North Sea in 1925, face swollen from hay fever, running on no sleep, scribbling equations that would quietly detonate the foundation of everything Newton and Einstein had built over 4 centuries. He was not trying to start a revolution. He was trying to solve a homework problem about electrons. What he found instead was this: reality, at its deepest level, does not exist in a definite state until it is observed. Before measurement, there is no position, no momentum, no there. 100 years later, with all of our telescopes and particle colliders and quantum computers, we still cannot tell you what that means. Subscribe, and let's stare into that gap together. Now, let's begin. Before 1925, the universe made sense. Not completely. There were loose threads, minor irritations at the edges of the equations. But the core picture was clean, elegant, and deeply reassuring. The universe was a machine, a vast, interlocking system of causes and effects running forward through time like clockwork. Newton gave us the blueprint. Every particle in existence follows precise laws of motion. Give me the position and velocity of every particle right now, and in principle, I can calculate every event that has ever happened and every event that ever will. The universe is not mysterious, it is merely complicated. Einstein shattered the clockwork, but only to rebuild it grander. Space and time were no longer separate and absolute. They bent, warped, merged into a single fabric called space-time. Simultaneity was relative. The speed of light was the ultimate speed limit. These were shocking ideas. But notice what Einstein kept intact: determinism. His equations of general relativity are perfectly precise. No ambiguity, no randomness. The distribution of matter and energy in space-time determines its geometry completely, which in turn determines how everything moves backward and forward through time without exception. Think of it this way. Newton gave us a chessboard with fixed rules. Einstein curved the board and made the pieces heavier. But the rules, the idea that the next move follows inevitably from the last, those rules survived. In 1925, that assumption felt unshakable. It had perhaps 3 months left to live. His name was Werner Heisenberg. He was 23 years old, and he was miserable. It was June of 1925. Heisenberg had been suffering from a severe hay fever attack so debilitating that his supervisor, Max Born, essentially sent him away on medical leave. He took a boat to Helgoland, a small rocky island in the North Sea, almost entirely devoid of vegetation, which meant almost entirely devoid of pollen. There, completely alone, face still swollen, he did what obsessed young physicists apparently do on remote islands. He worked. The problem consuming him was the atom, specifically, the behavior of electrons that no existing theory could fully explain. Bohr's model worked for hydrogen, but collapsed everywhere else. The equations kept producing numbers that did not match reality. Something fundamental was missing. Heisenberg made a decision that sounds simple, but was philosophically radical. He asked himself, what would Einstein do? Einstein had built relativity by stripping away assumptions that felt obvious but could not be directly observed, like the universality of time. So Heisenberg applied the same discipline to the atom. He resolved to build a theory using only quantities that could actually be measured, not the position of an electron between observations, not its path, its orbit, its trajectory through space. Those things, he argued, were stories we told ourselves. What we could measure were the frequencies and intensities of light that atoms emitted. So he built his mathematics from those alone. What emerged was something deeply strange. Position and momentum could no longer be represented as simple numbers. They became arrays of numbers, matrices, and these matrices did not obey the ordinary rules of multiplication. Specifically, if you multiply the position matrix by the momentum matrix, you get a different result than if you multiply them in the opposite order. In mathematics, this is called non-commutativity. Here is the clearest way to understand it. Put on your shoes and then your socks. Now reverse the order. You get a completely different outcome. With electrons, the order in which you ask questions about reality determines the reality you receive. Heisenberg reportedly finished the core calculation around 3 a.m. He described being so unsettled by what he found that he could not sleep. He walked out to the tip of the island and sat on a rock until sunrise. He had not found a better description of the electron. He had mathematically erased its right to exist in a definite state when no one was looking. Before we go further, We need to correct something. There is a version of Heisenberg's uncertainty principle that gets taught in classrooms, repeated in documentaries, and passed around as settled explanation. It goes like this. We cannot measure the position and momentum of a particle simultaneously because the act of measurement disturbs the particle. Our instruments are too clumsy. We shine a photon onto an electron to see where it is, and that photon kicks the electron, changing its momentum. The uncertainty is our fault, a limitation of tools, not of reality. This explanation is wrong, not partially wrong, fundamentally wrong, and Heisenberg himself knew it. The uncertainty principle does not describe a measurement problem. It describes an ontological condition, a statement about what exists, not about what we can access. Position and momentum do not simultaneously exist as sharp, definite values. They are not hidden from us by clumsy instruments. They are genuinely, irreducibly undefined until a measurement forces one of them into existence. The mathematics makes this unavoidable. The uncertainty relation delta x times delta p is greater than or equal to the reduced Planck constant divided by 2 is not an error bar. It is a statement about the structure of reality itself. The more precisely a particle's position is defined, the less defined its momentum becomes, not because we disturbed it, but because a particle with a perfectly defined position is a quantum state that mathematically cannot have a defined momentum. These two properties are not independent features, they are complementary faces of the same underlying entity, and sharpening one necessarily blurs the other. Now stop thinking about electrons for a moment. Think about your hand, every atom in it, every electron in every atom. Right now, none of those electrons has a precise position. Each one exists as a smeared probability cloud, a quantum fog that only resolves into something definite when an interaction forces it to. Your hand, at the level that actually matters, is a superposition of possibilities holding its shape through sheer statistical consensus. This is not a poetic metaphor. This is what the equations describe. And here is the consequence that no one in 1925 was prepared for. If particles do not have definite states before measurement, then the future cannot be calculated from the present. Determinism, the 400-year-old assumption that the universe is in principle perfectly predictable, was not an approximation. It was simply wrong. Physics did not take Heisenberg's matrix mechanics quietly. The formalism was correct. No one could argue with the predictions. But the theory offered no picture, no story, no way to visualize what was actually happening inside the atom. Matrices replacing trajectories, observables replacing existence. For physicists trained on the intuitive geometry of Newton and Einstein, it felt less like a theory and more like a calculation machine with the explanation removed. 6 months later, relief arrived from the Swiss Alps. Erwin Schrödinger, older than Heisenberg, more classically trained, and reportedly accompanied on his holiday retreat by a girlfriend whose identity remains unconfirmed to this day, produced something far more familiar. Starting from Louis de Broglie's idea that matter has a wave nature, Schrödinger derived an equation describing how a wave associated with a particle evolves smoothly and continuously through space and time. It was intuitive, it was visual, it was, in the language of the era, something you could actually imagine. Physics exhaled. Then Max Born read it carefully and delivered the uncomfortable clarification. The wave Schrödinger had described was not a wave of matter. It was a wave of probability amplitude. The square of its value at any point gives the likelihood of finding the particle there upon measurement. Between measurements, the wave spreads, interferes, and evolves. At the moment of measurement, it collapses to a single point. Schrödinger was not pleased. His response has become one of the most quoted lines in the history of physics. He said he did not like this interpretation and was sorry he ever had anything to do with it. In 1927, Paul Dirac demonstrated that matrix mechanics and wave mechanics were mathematically equivalent, two different languages describing the same underlying system, which meant the physics community now had two formalisms in perfect agreement with experiment and zero consensus on what either of them actually meant. That argument has not been resolved. It is still ongoing. Right now, among working physicists. Here is the problem that 100 years of the sharpest minds in human history have failed to solve. When a quantum system is left alone, its wave function evolves smoothly and deterministically according to the Schrödinger equation. A particle spreads into a superposition existing across multiple possible states simultaneously. So far the mathematics is clean. Then someone makes a measurement, and the superposition vanishes. The particle snaps into a single definite outcome. One result, out of all the possibilities, is selected. The question that has haunted physics since 1925 is this: what actually happens during that snap? What causes the collapse? Where exactly does the quantum world end and the definite classical world we experience begin? No one knows. This is called the measurement problem, and it is not a philosophical nuisance at the edges of the theory. It is a hole at the center of it. 3 serious attempts have been made to patch that hole. Each has costs that make physicists deeply uncomfortable. The first is the Copenhagen interpretation, assembled primarily by Bohr and Heisenberg themselves. Its answer to the measurement problem is essentially, do not ask. The wave function is a calculational tool. Asking what the particle is doing before measurement is asking a meaningless question. Predict the outcomes, match the experiments, and stop demanding a story underneath the mathematics. It works perfectly as a practical framework. As an explanation of reality, it deliberately offers nothing. The second is the many worlds interpretation, proposed by Hugh Everett in 1957. Here, the wave function never collapses. Instead, every possible outcome of every measurement actually occurs in branching, parallel versions of the universe that never interact with each other again. The mathematics is arguably the cleanest of all interpretations. The cost is accepting the literal existence of an infinite proliferating multiverse that is, by construction, impossible to observe or test directly. The third is the pilot wave theory, developed by de Broglie and later expanded by David Bohm. Particles have definite positions at all times, guided by a real physical wave. Determinism is restored. But the wave must influence particles instantaneously across arbitrary distances, a feature that sits in deeply uncomfortable tension with special relativity. Now add one more layer. In 1964, John Bell derived a mathematical theorem showing that no theory based on local hidden variables, no theory where particles carry predetermined answers and influence travel no faster than light, can reproduce all the predictions of quantum mechanics. Experimental tests, culminating in work that earned the Nobel Prize in 2022, confirmed Bell's inequality is violated. Reality is non-local in a way that cannot be explained away. We are not missing a detail. We may be missing something categorical, a concept that does not yet exist in our language for describing the world. 100 years, the most precisely tested theory in scientific history. And we still cannot tell you what it is describing. Here is what makes this more than a historical curiosity. The questions Heisenberg opened in 1925 are not sitting in philosophy seminars. They are colliding with the most advanced experimental data our civilization has ever produced. And the data is not making things simpler. In 2019, Google announced that its quantum processor had performed a specific calculation in 200 seconds that would take the most powerful classical supercomputer approximately 10,000 years. This was the first credible demonstration of what researchers call quantum supremacy. The processor works by exploiting superposition and entanglement, the same phenomena that have resisted conceptual explanation for a century. We are building the most transformative computational technology in human history on a foundation we do not fully understand. That same year, a team in Vienna conducted a double-slit experiment using molecules composed of approximately 2,000 atoms. Objects that large, by any intuitive measure, should behave classically. They did not. They produced interference patterns, the unmistakable signature of quantum wave behavior. The boundary between the quantum and classical worlds is not where we assumed it was. It may not be a fixed boundary at all. On the theoretical side, physicist Wojciech Zurek has proposed a framework called quantum Darwinism. The central idea, and this is a hypothesis under active investigation, not established consensus, is that classical reality emerges when information about a quantum system leaks into the surrounding environment and gets redundantly recorded across many independent fragments of that environment. What we experience as objective reality may be the subset of quantum information that survives this selection process. It is a compelling reframing of the measurement problem, but it remains contested and unconfirmed. Meanwhile, the James Webb Space Telescope is delivering data from the earliest epochs of the universe, periods when quantum fluctuations were directly seeding the large-scale structure of everything that exists today. And the Large Hadron Collider has systematically failed to find the supersymmetric particles that the most mathematically elegant extensions of the Standard Model predicted. The beautiful theories are losing to the data. This is the pattern emerging across every frontier. The deeper we look, the more precisely we measure, the stranger and less resolved the picture becomes. Heisenberg's island is getting larger, not smaller. We have spent the last several minutes talking about electrons and islands and mathematical matrices. Now let's talk about you. Your body contains approximately 7 billion atoms. Every single one of them is governed by the equations Heisenberg wrote on that island in 1925. Every electron in every atom in every cell of your brain right now does not have a precise position. It exists as a probability distribution, a quantum fog that resolves into something definite only through interaction with its environment. The neurons firing as you process these words are not classical switches flipping between clean binary states. They are electrochemical systems built from quantum mechanical components, operating in warm, wet, noisy biological tissue. Whether quantum effects play any functional role in cognition remains genuinely open. Researchers Roger Penrose and Stuart Hameroff have proposed that quantum processes in structures called microtubules inside neurons may be relevant to consciousness. This hypothesis is highly contested and lacks direct experimental confirmation. But the question it raises is real and remains unanswered. Here is the version of that question that no interpretation of quantum mechanics has cleanly resolved. If reality requires observation to become definite, if the wave function collapses only through measurement, then what counts as a measurement? A detector? A human eye? A conscious mind? And if consciousness is required to collapse the wave, then before conscious observers evolved in this universe, what was collapsing anything? This is not mysticism. This is a question that follows directly from the mathematics. The universe apparently ran for nearly 14 billion years before anything looked at it. What was it doing? Before we reach the conclusion, intellectual honesty requires a clear accounting. Here is what is not in dispute. Quantum mechanics is the most precisely verified theory in the history of science. The predicted value of the electron's magnetic moment matches the experimentally measured value to 12 decimal places. That is the equivalent of predicting the distance from New York to Los Angeles and being accurate to within the width of a human hair. Transistors work because of quantum mechanics. Lasers work because of quantum mechanics. MRI machines, solar cells, LED screens, GPS satellites. None of these exist without the equations Heisenberg and Schrödinger wrote in 1925. The theory's practical power is completely beyond question. Here is what remains genuinely unresolved. The measurement problem has no agreed solution. The interpretation question, what quantum mechanics is actually describing about reality, has no consensus answer among working physicists. The boundary between quantum and classical behavior has no precise location. The unification of quantum mechanics with general relativity remains the deepest unsolved problem in theoretical physics. These are not gaps that popular science is reluctant to admit. They are openly acknowledged in the technical literature. The theory works with breathtaking precision, and no one can fully explain why or what it means. Both of those things are true simultaneously, much like a certain principle we discussed earlier. So where does this leave us? In the 1930s, the next generation of experiments will stress-test quantum mechanics at scales and energies we have never reached. The High Luminosity Large Hadron Collider, coming online around 2030, will produce collisions at intensities 10 times greater than anything achieved before, probing the structure of matter at distances where quantum mechanics and gravity may finally be forced to interact in measurable ways. Also in the 1930s, quantum computers operating at meaningful scale may allow us to simulate quantum systems too complex for any classical machine, potentially revealing new phenomena that current theory does not predict and cannot explain. That gap between prediction and observation is historically where revolutions begin. Proposed experiments in quantum gravity, particularly those designed by researchers Sugato Bose and Vlatko Vedral, aim to test whether gravitational fields can generate quantum entanglement between massive objects. If confirmed, this would be the first direct evidence that gravity itself has a quantum nature. It would mean spacetime, the fabric Einstein described, is built from something that obeys Heisenberg's principle at its foundation. We do not know if any of these experiments will resolve the measurement problem, settle the interpretation debate, or unify our two greatest theories. They may instead open questions we do not yet have language to ask. That has been the pattern since 1925. A 23-year-old on a barren island, running on no sleep, erased the definite existence of the electron. 100 years later, we have built an entire technological civilization on the equations he wrote that morning. We have confirmed their predictions to a precision that borders on the unreasonable. And we still cannot tell you what an electron actually is when no one is looking. Perhaps that is not a failure of science. Perhaps that is science working exactly as it should, pulling back one curtain only to find another, and having the honesty to say so. The universe has kept this secret for 14 billion years. It does not seem to be in any hurry to give it up.